Being too young to rent a car at the time, I took a motorbike 50 kilometers outside of Townsville, Australia to visit this facility, to learn about the current cutting-edge science in coral restoration, specifically about the possibility of breeding heat-resistant corals that could continue to support reefs in much hotter oceans. In the ocean, corals commonly reproduce by spawning. They release millions of eggs onto the reef that can then be fertilized before settling as new colonies. Corals spawn based on very specific environmental cues of temperature, moonlight, and tides. The Sea Simulator is a facility that can be compared as a much more advanced and versatile version of my home experiment. But here, everything is done with razor precision and sometimes on a massive scale.
Yeah, so each one of those tiny little specks you see is a fertilized embryo. What will happen is we keep it inside these tanks for about 7 days or so while it fertilizes from the night before into a larvae, a free-swimming larvae that's cannulated. And then eventually it'll become competent, which means it's ready to settle onto a reef structure. These are about 2 years old now. So this room here is where we grow out the recruits. After we settle them from larvae, they turn into coral recruits, and we grow them out in this room for various experimental purposes, or to grow them up into sexually mature adults or sexually mature F1s. These aren't frags. These have all actually been grown by sexual mature
from those tiny little eggs.
Yeah, exactly. So one of those tiny eggs is then settled onto conditioned aragonite plugs. So these have been conditioned in the system with the crustose coralline algae, which, like I said, is a settlement inducer. So we have a PVC tray like this into a settlement tank filled with these plugs, and then we release larvae into the tank, and if they're competent, they'll actually grow onto these plugs. As you can see, very, very tiny. This is a Cropora millipora from December 2023. So these corals are going to grow in a few years into the size that we've just seen, and then in 5 or 6 years they'll be sexually mature adults, as long as we...
Whoa, that's so cool.
They're tiny, aren't they?
So it's like Supercoral iteration 1?
Yeah.
Okay.
Yeah. And then the goal of a lot of these breeding programs in aquaculture is to get the F2s, which means the filial second generation, which is the offspring from the F1s.
Okay.
And what that means is that you've closed the life cycle because you've completed the whole life cycle of that species in captivity, which we have for a lot of these species that serve here.
The facilities mimic ocean environments so flawlessly, corals here actually spawn as they would on a reef, unaware they aren't in the ocean. Not only that, but Lonnie explained to me that he and his team are even able to trick corals into a 6-month offset of spawning, allowing for restoration work to continue throughout the off-season.
Could we get the corals to spawn when we lot? Could we get them to spawn in winter, which is 6 months before they normally would in the wild? And the answer is yes, which is fantastic.
Really? Wow, that's so cool.
Yeah. Not only is this 6-month offset, it's 5 hours offset, which means we get them to spawn 5 hours before we shoot.
Okay.
So we're not hanging around till midnight. We're actually getting them to spawn around 2 p.m. So workability is a lot better.
Right.
And we also managed to settle them into those juvenile recruits, which we've seen.
Right.
Which means, again, we've closed the life cycle of more species, but we've done it, 6-month offset.
So these are the F1s on that offset.
Yeah.
That's so cool. So you're able to accelerate the science by skipping the downtime.
Yeah.
So from collective wild coral species, the CSIM is able to complete and repeat the entire life cycle of coral in captivity all year round. But corals grow slowly, and climate change is exponential, so the current scientific frontier of coral restoration is about exploring techniques to actually speed this process up.
So this is one of the projects we do on asexual reproduction of corals. So we've been exploring microfragmentation, which is when you take a little small frag from a colony, and when you make a microfrag, which is the size of your little fingernail, about 8 by 8 millimeters, in certain species, it kickstarts some rapid growth. We'll get a better footage of it. So this is a concrete pyramid with nearly 100 microfrags of platygyra from the same genotype. So these have undergone rapid growth when they were first glued onto this structure. And what happens is that when they meet each other, they actually fuse because they're the same colony, essentially. And once they fuse, the idea here is that they'll start pulling their energy, or switching their energy rather, from growth into reproduction. So they'll thicken up and then start to develop gametes inside the colony. So that was generated from wild broodstock. That's 8 years old now, and that's how big it is. Can compare it to the
From the other, and that one's only 2.
That's 3 years old now, I thought.
So less than half, and it's like way bigger.
So there was talk at some stage to try and investigate that, because if it was a gene you could turn on in just normal corals, you could get them to undergo fast growth, which would be obviously have quite a lot of mean